This is the screencast for section 5.1, example 1. So at this point in the course, we are going to be moving backwards. We've been taking derivatives and using slopes of tangent curves. Now we're going to move backwards into the antiderivative realm. Now, if you remember way back when we started derivatives, we did it step by step. We found the limit as h approaches 0 of f of x plus h minus f of x all over h, and then we went forward from there. Well, we're going to do the same thing with antiderivatives. So we're going to start slow and start complicated and then get to the easy stuff. So you have to be patient, and all of this is required. It will all be on the AP exam, otherwise we wouldn't teach it. So here we go. Estimating with finite sums. So the idea of this antiderivative starts with, what does it mean? What is it used for? Derivatives are slope of tangent curves. Antiderivatives are area under curves. So if we're talking about position and velocity and acceleration, velocity is also speed or rate, and you know this as distance equals rate times time. Well, in the past, you have used distance equals rate times time as only in the circumstance of a constant rate. So here you're given the velocity graph, your rate is constant, and then if your time was from 7 to 9 minutes, your total is 2 minutes, so your distance, total area here, equals your rate 75 times 2, so 150. Now, what we're going to start to study is what happens when the rate or velocity changes. How do you estimate that? Well, we have this method called the rectangular approximation method. I know this looks overwhelming, I'm going to explain it. So the rectangular approximation method says we're going to take the area under this curve and piece it together with little tiny rectangles. Now hopefully those rectangles will become infinitely thin, and therefore we'd get more and more accurate, but for right now we don't have that option. That's later on. So what we're going to use is a left rectangular approximation, a middle rectangular approximation, and a right rectangular approximation method. That's what the M is for. Okay, so the left, we have your basic y equals x squared. Start with something simple. We are going to study the area under that curve from 0 to 3. This problem doesn't tell us how many pieces to divide the area into. I'm going to choose 6 pieces. So basically we're going to take this distance equals rate times time and use 6 different rates. The rate according to each of 6 different x values, the left side of each of these intervals. So if I take from 0 to 3 and I divide it into 6 pieces, basically I'm taking a division at 0, 1/2, 1, 3/2, 2, 5/2, 3. Each of them has a width of 1/2. So there's your time is 1/2. The rate is determined by the y value. So I'm going to plug in the left side of each of those rectangles. So 0, f of 0 times 1/2. So here's your rate times time, plus another 1/2. So there's your other time. But now the left side of that rectangle is at 1/2. So f of 1/2 is your new rate times time, plus another rate of 1 times 1/2, then f of 3/2, then f of 2, and then f of 5/2, and then we won't use f of 3. F of 3 is not the left side of any one of these rectangles under the curve. So if we plug in each of these x values to our function, we find out the height, the y value. The height, again, is our rate, our velocity. So our rate times time plus rate times time plus rate times time, all of those added together would be our final estimate of our distance. Distance equals rate times time. So now f of 0 is 0 squared, f of 1/2 is 1/2 squared, f of 1 is 1 squared, etc. So then I multiplied all those together, and really you can factor out the 1/2 since they all have the same width or the same time span for each mini rectangle. I can factor that out, and I get about 6.875 units. That is how far the particle has moved. Again, distance equals rate times time. Distance, 6.875 units, is approximately equal to each of these rates, each of these 6 rates for 1/2 of a minute each or something. Now MRAM is going to take the middle of each of these divisions. So the middle, instead of using 0 and 1/2, I'm going to use the middle of those, 1/4. Or between 1/2 and 1 is 3/4. Between 1 and 3/2 is 5/4, and you can see the pattern. 1/4, 3/4, 5/4, 7/4, 9/4, 11/4. So I'm going to use each of those x values to find the new rates according to the middle of each of these rectangles. So those are the new heights. I'm going to plug each of those x values into our x squared. So f of 1/4 is 1/4 squared, f of 3/4 is 3/4 squared, etc. And I get that it's approximately 8.9375 units. Now, as you may have guessed, this one's going to be pretty close because you can see I have a little bit of overestimate for each underestimate or blank space missing in these little rectangles that I've used to approximate the area under the curve. Whereas our LRAM was definitely an underestimate. There's all these voids in our estimate of area. Now our RAM in this case is going to be an overestimate. We're going to use the right side of each of these rectangles. So we're going to start out with 1/2, the right side of the first rectangle, plug that in to get that rate. Then 1, then 3/2, then 2, then 5/2, and then we are going to use 3 for this one because it's the right side of the last rectangle. And that's going to be 11.375 units, which is definitely an overestimate because those rectangles would overlap the area under the curve. To now try problem number 3, says that a particle starts at x equals 0 and moves along the x-axis with velocity t squared plus 1. So there's your rate, how we're going to find those y values for the rate for each of those rectangles for time t is greater than or equal to 0. Where is the particle at t equals 4? So we started out at position 0. It wants to know how far did it move after 4 seconds, so therefore where is it? Is it 8 units out? Is it 27 units out? We don't know. Approximate the area under the curve using 4 rectangles of equal width and heights determined by the midpoints of the intervals. So those midpoints of the intervals means we're going to use LRAM, MRAM, or RRAM. That's right, MRAM, the middle rectangular approximation method. Alright, so I'm going to draw first of all what this looks like. Our velocity curve is t squared plus 1, which means it's a parabola that has a vertex at 0, 1. And it said to use the span from 0 to 4 and divide that into 4 rectangles. So here it is, and we're going to use the middles of each of those. So I'm going to use not 0 and 1, but 1/2, not 1 and 2, but 3/2, not 2 and 3, but 5/2, and then 9/2. So I'm going to use the middle of each of those intervals of the 4 rectangles we divided the space between 0 and 4 into. So the approximate area under the curve then, each of these rectangles has a width of 1, so I can put that on the outside. And then now I'm going to plug in to my velocity curve each of my middle x values. 1/2, 3/2, 5/2, and 7/2. Which means if I'm plugging them into v, I need to plug them into t squared plus 1. So I'm looking at each of those x values plugged into the velocity function. Again, 1/2, 3/2, 5/2 squared plus 1, and then finally 7/2 squared plus 1. And then when I do a little bit of simplification, I get that the answer is 25. Now, of course, that's just an approximation. It is going to be pretty close, though, because I have some overlap and some void, or underlap, if you will, for each of those rectangles that I drew. So now, what does this 25 mean? Well, the 25 means, remember, distance equals rate times time. Each of these rates times the 1 second each. So we went 5/4, I don't know, meters per second for 1 second, 13/4 meters per second for 1 second, and 29/4 meters per second for 1 second, etc. Distance equals rate times time. So this is a distance. The 25 means the particle moved about 25 units from time 0 to time 4, which I'm calling seconds. The problem didn't really label it as anything. So then that means the question, we haven't answered the question yet. It says Where is the particle at t equals 4? Well, the answer technically is 25 units, but that's only because it started at 0 units. The particle moved 25 units, which means since the particle started at x equals 0, position 0, at time 0, the particle is now at 25 units. See, if the particle would have started at maybe position 10 and moved 25 units, it would now be at position 35. So it just depends on where it started. 25 is the amount that it moved.